Hello everybody, this is Yousuf Siyabi. In this final update, I'm going to talk about simulating projections of complex block polymer morphologies. And before I start, I would like to thank my sponsors, the online RU program at Texas A&M University, and also my collaborators, Dr. Ned Thomas, Vivek Subramanian, and Shuyan Feng. What is phase separation in block copolymers? Block copolymers consist of two or more types of monomers, and phase separation happens when these block copolymers separate into domains caused by the self-assembly of the monomers. These domains have been studied and characterized by different periodic morphologies as a function of different parameters such as temperature, volume fraction, solvent, concentration, and many other parameters. And this picture here shows the different morphologies of diblock polymers that consist of polymer A and polymer B as a function of volume fraction and keeping all other factors constant. So as you can see, increasing B volume fraction, we start to move from spheres to cylinders and then gyroids and then laminar morphology, and then we reverse the compositions. So laminar morphology occurs around a volume fraction of 0.5, and the most complex structure here is the gyroid structure, which also called biocontinuous structure. It includes double gyroid and double diamond structures, which we are interested in visualizing. So our goal was to use the VISO software to create 2D and 3D projections through complex microstructure such as double gyroid and double diamond to simulate TEM images and compare these to the literature. But unfortunately, our group was not able to purchase the software on time. Thus, I'll be using the 3D structures that were designed by Shuyan Feng, who is one of the group members, and I'm going to focus on the double gyroid structure since they both have the same way of analyzation. There are many methods that I'm going to use to achieve this goal, and ImageJ is one of these methods that I'm going to use to analyze the structure by finding the fast Fourier transform of the projection. I'll also be using TIMSIM tool, which is designed to picture the 3D structures of different block polymer morphologies. TIMSIM contains TEM and atomic force microscope images that were simulated using volume projections. Also, I'll be using the Miller indices visualizer, which is used to visualize the planes in different lattice structures, simple cubic, body-centered, or face-centered. Miller indices are used to specify the orientation of the crystal plane in a lattice. Miller indices are denoted as HK and L, and the crystal plane is denoted as HKL. So for example, we call it 111 or 100, and these are also called the volume projections. And as you can see here in the picture, these are different projections, and each projection has a different number. And in order to view the 3D structures that were designed by Shuyan, I used the vProject website, which allows me to rotate the 3D structure, change colors, and many other options. For the double gyroid structure, I'll be presenting three planes. First one is 100 and 110 and 111 plane. And this picture here shows the 100 plane in the body-centered structure. And the other figure here shows the 100 projection of the double gyroid structure. And this plane has a fourfold symmetry, and it belongs to what they call the B4MM space group. And we can compare this to a real double gyroid lattice. As you can see here, this is a picture taken using a TEM, transmission electron microscope, of a BSPI PS block polymer, and this is and the projection is 100 projection, and this actually picture shows the other picture here shows the fast Fourier transform of that TEM image, and this actually created by me using image J, and from that we can see the B4MM structure here, the B4MM space group, which actually means that this has a fourfold structure or fourfold symmetry. The next plane is 110 plane. This is the 110 plane in a body-centered structure, and the other figure here shows the projection of a simulated double gyroid structure, actually this plane has a twofold symmetry, and it belongs to what they call C2MM symmetry space group. We can compare that to a real 1-0 projection of the same plug copolymer used before, and the picture actually shows a twofold symmetry, and also the FFT also shows a twofold symmetry. This picture here shows the 1-1-1 projection in the body-centered structure, and the other picture here shows the simulated image of a 1-1 projection of a double gyroid structure, and it actually shows what we call the B6MM symmetry, or also called six-fold symmetry. We can also compare that to a real 1-1-1 projection of the same plug copolymer use, and we can see that after actually obtaining the fast Fourier transform of that, we can see the same six-fold symmetry. The shallow projections in the TIMSIM tool can be used to visualize the complex structures such as double gyroid or double diamond structures, and TIMSIM tool was used to simulate the double gyroid structures for specific Miller indices and slice depth. However, unfortunately, the tool doesn't have all Miller indices in it. However, the good thing is that you can change the slice depth by a 5 increment of depth. Unfortunately, SimTim tool doesn't include the planes we discussed, which are the 100, 110, and 111. So I chose the 112 plane, and this actually shows the body-centered structure. And also this picture here shows the shallow projection at slice depth of 1. And here we are increasing the slice depth by 10% by cutting through the sample, and then we go more deep to 15% and so on until we reach 45%. This is the maximum slice depth we can reach, because after that we actually repeat the same shapes. The importance of shallow projections, as you can see, that it helps visualizing these complex structures. In conclusion, there are some key takeaways. The double gyroid structure was synthesized using volume projections, and the projections were studied were 100, 110, and 111, and these are the most important projections actually. And the observed image symmetries for each projection are B4MM, C2MM, and B6MM respectively. The TIMSIM shallow projections are useful for visualizing DG complex structures. And thank you for listening.